Hello, I'm so glad you've joined me for this next video in the series. As you know, this is the Essential Skills series, focusing not on content, but on the skills you need for Physical Science Paper 1, that's the physics paper. I'm Dr. Derek Fish. I'm Director of Unizulu Science Centre at the University of Zululand, and it's my pleasure to present this to you. We're now going to be moving on to part 6.4, continuing to look at equations and how to solve equations, but first focusing especially on the equations for momentum that come up in question 4 in your paper. In your booklets, this will be on pages 49 to 51. So you should follow in your books while you watch this video. But as usual, let's start on page 3. Just inside your front cover, the contents page, and let's see where we are in this course. So this is a compressed contents page. We're looking at the section on equations. And if we expand that, we're looking particularly on the equations that govern momentum. And these come up particularly in question 4 in paper 1 of your matric science paper. Once again, a comment from the examiner that learners still cannot work with scientific equations and formulae. That's why we've got such a big section on the skill of solving equations. Looking on page 4, looking at the curriculum, momentum, of course, comes under the mechanics section, and it only comes in grade 12, usually at the start of grade 12. You'll see over here momentum and impulse, and also Newton's second law expressed in terms of momentum, conservation of momentum, and elastic and inelastic collisions. The prescribed experiment is to look at the conservation of linear momentum. This is normally a shorter question. It's question 4, and averaged over the last 3 papers, it's averaged around 12 marks. Fewer marks, but still very important. Looking at the last 3 years of exam papers, the momentum questions have been quite different. 2020, it was a straightforward collision between 2 moving objects. 2019, it was a bullet moving through a fixed wooden block and obviously slowing down as it did. 2018, it was a girl on roller skates throwing a parcel away from her and consequently moving in the opposite direction. And also on page 5 in your booklets, what particular skills will you need for this section? Well, of course, we're focusing on solving equations. And in particular, you'll need scientific notation. Make sure you can do that. Conversion of units, and also changing the subject of the formula. This is probably the most important skill for the equation section. Get lots of practice and make sure that you can do that. Again, a comment from the examiner. Severe lack of skills is evident. Mathematical, conceptual understanding and integration of topics. Also free body diagrams, graphs, and equations. So we understand that many of you struggle with equations, and that's why I'm here to help you. So in order to understand the equations, particularly this momentum equation, P equals mv, momentum equals mass times velocity, let's revise some of the basic theory. But please remember, this video series is not intended to replace your textbook or your teacher. It's simply to sharpen your skills. So please make sure that you go through momentum very carefully in addition to following these videos. So as we start thinking about momentum, let's have a look at this executive desk toy, which is often called Newton's cradle, that you saw the cats playing with. When you lift a ball on one side and drop it, it transfers the momentum through to the other balls like that. Now, let's consider this in the light of momentum. Maybe to start with, let's get rid of 3 of the balls and start with just 2 so we can focus on what's happening here. And you can see that the second ball is stationary. When I drop the first ball, it transfers its momentum to the second one and it comes to rest. Now, in a perfect system, it would come completely to rest, but of course, this is not a perfect system. If we put other balls between it, then that momentum is transferred all the way down the line until the last ball is knocked off. Now you can see it carries on going for quite a while, so it doesn't lose too much energy, but of course, eventually it does come to rest, so it's not a perfect system at all. So if I drop just one ball, you can see just one ball comes off the other side. I want you to think for a bit what would happen if I actually dropped two balls. Maybe take a moment to think about this. Teachers, maybe pause the video, let the class discuss this. But when I drop two balls, then two balls come off the other side. So momentum must be conserved. If you've got two masses times velocity on one side, we need two masses times velocity on the other side. And I can try with three balls, and you can see three balls are transferred, and so on, all the way down. Now you can see conservation of momentum very nicely. If I take two balls from one side and one ball from the other side, just leaving two in the middle, and I drop these, notice how the two balls are transferred from one side to another. It's quite quick, so let me allow you to see that again. So two balls on your left-hand side, one ball on your right-hand side, and you can see how that is transferred. The momentum must be conserved. If I drop just one ball from each side, then you see these balls just bounce backwards and forwards. We'll talk later about elastic and inelastic collisions, and this collision is almost perfectly elastic because they are hard steel balls that don't deform or squash very much when they hit each other. So let's leave the kittens to play with Newton's cradle, and let's have a look at some of the basic theory behind momentum, and particularly the mathematics and the equations. So we're on page 49 in your booklets, and at the top of page 49, we consider the variables which come up in the momentum equation. There's 6 of them. Most of them are very familiar to us by now because they come up throughout mechanics. So mass in kilograms, we're very familiar with. Velocity in meters per second. Please remember, although most cars measure velocity in kilometers per hour, in physics we measure it in meter per second. And it's a useful rule to remember that 1 meter per second is 3.6 kilometers per hour. So a meter per second is faster than a kilometer per hour. We use the subscripts I and F for initial velocity and final velocity. Now we have this new variable, momentum P, and the unit is kilogram meters per second, because it's a product of mass in kilograms and velocity in meters per second. Delta T, time in seconds, and the average net force F net in newtons. Now, why do we need to consider mass times velocity? Why isn't velocity enough? See, momentum has a lot to do with collisions, and in collisions, mass is very important. So even if a big truck is moving slowly, it's difficult to stop because of its large mass. Even if a very light bullet is moving fast, it's difficult to stop because of its large velocity. The momentum gives you a measure of how difficult it is to stop an object. Now, of course, in a collision, the size of the object makes a big difference, as you can see in this collision between cars and trucks. And I think you can imagine that it would be better to be the driver of the truck in this accident than the driver of the car. And with a momentum collision, the heavier object always wins. And I think you can imagine that when these two collide, the heavier object is definitely going to win. So here's an exercise you probably shouldn't try at home. You can see these two decided to have a momentum collision with large soft balls to protect themselves, but because the guy is heavier, although they collide at about the same speed, the girl gets thrown backwards. So it's all about the mass. Let's have a look at another example a bit slower. You can see they collide at about the same speed, but because of the larger mass of the guy, the girl gets thrown backwards with disastrous consequences. So we have to consider the masses, because a heavier mass means you have more momentum, and which means the lighter object will suffer a larger change in momentum. Now, this is great to investigate using another one of these wonderful PHET simulations. This one is called Collision Lab, and teachers, it is in your teacher pack. So please take the time to investigate things by yourself, that you can manipulate the variables and the values. So let's just have a look at that question of the importance of mass in a momentum collision. So I've chosen two. You can have more, and we can adjust the masses. We can also adjust the velocities. But at the moment, I've got two objects of the same size, and you can see that when they collide, all the momentum is transferred from body 1 to body 2. Now, what I can do with this app is I can make 2 much bigger, and you can see I'm increasing the size of 2. So it's now 6 times the mass of object 1. And you can see now when there's a collision, 1 actually bounces right back, and 1 would undergo a much bigger change in momentum. And 2 moves off, but very slowly. Let's look at a different scenario. If we give 2 some velocity as well, so they have about the same velocity. Now this would be like the case of that boy and girl colliding that you saw in the video. So let's see what happens. And you can see a very large force is exerted on 1, and 1 is thrown back very strongly, whereas 2 keeps going in the same direction, just slowing down. But let's have a look at that again. You can see that size really does make a difference. If I took the second scenario and made the 2 about the same size, you can see that really they would both go back with about the same speed. I really encourage you to use this collisions lab to investigate momentum collisions, because you can learn a lot. And as I've shown you here, size and mass really does matter. I'm sure you agree that that simulation really helps us to understand momentum. Now, lower down on page 49, we have the principle of conservation of linear momentum. Now, that's a bit of a mouthful, but it simply means that momentum before a collision is equal to momentum after, or momentum is conserved. Linear simply means straight line, and you can be glad that at school and in matric, you'll only deal with linear or straight line collisions. They get much more complicated when they're 2-dimensional or even 3-dimensional. So we use PI for the initial momentum or the momentum before, and PF for the final momentum or the momentum after. When you have 2 bodies involved, we would probably use the sigma notation to say the sum of all the initial momenta must be equal to the sum of the final momenta. So the momentum of A can change before and after, but the sum of the momenta of A and B will stay the same. And we can write it out in that longer notation. Actually, only 6 variables there because, of course, the masses of A and B are the same on both sides. And at school level, you probably won't be dealing with questions which involve a change of mass. In the exam questions, inevitably, one of these variables will not be given. For example, you might be asked to calculate the velocity of ball B after the collision. You'll simply fill in all the values that you have and solve the equation for that particular variable. Now, once again, let's use our collisions lab, and let's take these 3 examples and let's investigate what happens in these 3 collisions. So let's use collisions lab to model those 3 examples of collisions that are in the middle of page 49 in your books. So please follow in your books. So we have 2 objects of the same size. They're 1 and 2 on the screen, but they're just called A and B in your book. In the first example, the one on the left, A is moving with some velocity, whereas B is stationary. If I allow the simulation to run, you can see the first ball comes to rest and the second ball moves off with the same velocity. We're assuming that the collision is 100% elastic, more about that later, and that no energy is lost at all. Now, what's useful is we can also put this on slow motion, and we can see exactly what happens. And in the collision, all the momentum is transferred from body 1 to body 2. So that's the first example. It's also quite useful to take a look at the momentum diagram. And you can see in this diagram, before the collision, only object 1 has any momentum because object 2 is stationary. So the total momentum is just the momentum of object 1. And you can see that that momentum is transferred from object 1 to object 2 in the collision. The other thing we can do with the simulation is put in the change of momentum and just watch. It happens very quickly at the moment of collision. At the moment of collision, you'll see the change in momentum, and both objects experience the same change in momentum because, of course, that must be conserved. Now, let's move on to the second example where you've got 2 objects going towards each other. So I'll just separate them a little bit. It's easy to do. So let's just make the velocity of object 1 1 meter per second, and object 2 will make it 1, but in the negative direction, so -1. You can see by the velocity vectors that the 2 velocities are the same. Now, you might be wondering what happened to the black arrow for total momentum. But of course, total momentum is now 0 because the momentum of 1 and 2 are equal and opposite. They have the same masses and equal and opposite velocities. So we can imagine what happens in the collision, seeing it in slow motion here, and you can see they simply change direction. Let's see it at normal speed again, and the two of them simply change direction, and you can see the velocities change direction there. So there's no change in total momentum, which is 0 before the collision and also 0 after the collision. And let's look at the third example. We have object 1 coming up behind object 2, and we're going to change object 2's velocity to a small positive velocity. So object 1 is going to catch up with object 2. Look at the momentum diagram here. You can see the total momentum is the momentum of 1 plus the momentum of 2. Momentum is a vector, so we must do vector addition. If we allow this to run, we can see what happens. So a lot of momentum is transferred from 1 to 2. And again, I encourage you to watch what happens in the change in momentum vectors, which you see at the top there. How the momentum from 1 is largely transferred to 2. So those are the three examples which you see in your booklet. Of course, there can be lots of other possibilities. These are three examples with equal masses, but the differences of masses and of velocities will depend on the outcome. Just remind you again that these are all perfectly elastic collisions. We'll look at inelastic collisions a bit later. So having looked at the conceptual understanding of momentum and introduced the basic idea, let's turn to the mathematical side, and particularly the equations which you need to know for your matric exam. Now, as always, you don't need to learn these equations by heart. They are given to you on your data sheets, but you do need to know where to find them. Now, in your booklet, your data sheets are on page 38 and 39, with the constant sheet on page 40. If you turn to page 38, you'll see the second section of equations is called force, and it contains the equations for question 2 on Newton's laws, but also for question 4 on momentum. And there's three equations we're going to look at: the definition of momentum, P equals mv, the change in momentum, delta P equals mv final minus mv initial, and the impulse momentum theorem. Now, on your page 49, we lay out these three equations. I don't want to spend time now deriving them. Please talk to your teachers and go to your textbooks. I just want to look at how to implement these in solving exam questions. The first one is quite obvious. The change in momentum is simply the final momentum minus the initial momentum. The mass stays the same. So delta P, the change in momentum, is mv final minus mv initial. Or taking out m as a common factor, it's the mass times delta v, the change in velocity. Now, this allows us to represent Newton's second law, which you'll remember is force equals mass times acceleration, in terms of the rate of change of momentum. So going through it, F equals ma, but of course acceleration is just delta v over delta t. It's the change in velocity over the change in time. I've just replaced acceleration, change in velocity over change in time. Now you'll recognize that term from there, and so we can replace that term with delta p, the change in momentum. So we end up with this equation that the net force, average net force, is the change in momentum over the change in time, or the rate of change of momentum. That's assuming that the mass stays constant, but at school level it usually does. Now we can rearrange that, just multiplying both sides by delta t, to give us the equation for impulse. And the impulse momentum theorem says that the average net force times the time is equal to the change in momentum. Please notice that impulse is not the force, it's the whole term on the left. It's the force times delta t. Now, that impulse momentum theorem is the science behind why we have airbags in motor cars. The airbags come explosively out of the dashboard of the steering wheel, but what they're actually there for is to provide a soft cushion for your head. So if the car hits an obstacle, you'll be thrown forward according to Newton's first law of motion. And instead of hitting a hard steering wheel and coming to rest very quickly, your head hits a soft cushion. and it takes much longer to come to rest. If you extend the time of the collision, you reduce the average impact force. You can see it more clearly here. The force is equal to the change in momentum. Now that will be fixed for a certain collision speed, but if you can increase the change in time, then it will decrease the force which is experienced by your head. And of course, that's exactly what you want to do in a collision. Now you can see it very nicely in this demonstration. An egg is thrown at a plastic sheet. And although the egg is thrown as hard as this guy can, and although it comes completely to rest in a forward direction, because it takes so long to decelerate, because delta T is so large, the force experienced by the egg is not that great and the egg doesn't break. And this is the principle of the airbag. Now, at the bottom of page 49, just to finish off a last bit of theory, we need to distinguish between elastic and inelastic collisions. Now, an elastic collision is one like the Newton's cradle. In a perfect Newton's cradle, no kinetic energy would be lost and the balls would continue bouncing forever. We know, of course, that's not the case, but a Newton's cradle is very close to a perfectly elastic collision. In an inelastic collision, the objects colliding are deformed, they are squashed. And you can see here the two cars will actually come to rest. So all the kinetic energy they had before the collision is lost. Now, of course, lost is not the correct word. It's changed into other forms. It's changed into heat energy, into sound energy, and into other forms of energy which are not particularly useful and which, of course, are very damaging. Now, most car collisions are actually partly inelastic. So you can see after the one car hits the other, it doesn't stop moving entirely. The two move off together, but a lot of energy is lost by the deformation which happens. Now, it's important to know, you can see it in the summary. In both types of collisions, momentum is conserved. Whether the collision is elastic or inelastic or something in between, momentum is always conserved, but kinetic energy is not. Kinetic energy is only conserved in a perfectly elastic collision. In a perfectly inelastic collision, we'll find it's not conserved. And in fact, some of it will be lost because it's converted to other forms like heat and light and sound due to the deformation of the bodies. Once again, our collisions lab is going to allow us an opportunity just to change the elasticity of the collision using this slider and investigate what a difference it makes to the collision. So we're going to recreate those three examples in the middle of your page 49, but look at them for elastic and inelastic collisions. So starting with elastic collisions, the first example shows ball 1 colliding with a stationary ball 2, and the momentum is transferred from ball 1 to ball 2. Now, if we make it an inelastic collision, we can see something quite different takes place because the balls stick together after impact and move off together. So you can see something different already in the momentum diagram. Let's just look at that again. Let's try it a bit slower. So the momentum of one is shared between the two afterwards because they stick together. Now, this doesn't tell us very much about kinetic energy, but we can actually ask PHET to tell us the kinetic energy before and after. You can see total kinetic energy before, which is obviously only from ball 1, because ball 2 is stationary, is 0.25 joules. In the elastic collision, kinetic energy is conserved, and you can see the kinetic energy afterwards is still 0.25 joules. Let's look at the inelastic collision, 0.25 joules of energy before, but only 0.12 joules of energy afterwards. So although momentum was conserved, kinetic energy was not, because some of it was converted to other forms by deformation of the objects which collided with each other. Now, most collisions in real life are a mixture, so we could put this as maybe 50% elastic, 50% inelastic, 0.25 joules of kinetic energy before, and 0.16 joules of kinetic energy after. Momentum is always conserved, but kinetic energy is lost or converted to forms which are not useful. Let's look at the second example, go back to elastic collisions, and let's take ball number 2, move it to the right, and let's give it a velocity which is equal and opposite to ball number 1. Okay. So in an elastic collision, again, total momentum is 0 because the two momenta are equal and opposite. If they collide and bounce off each other, total momentum afterwards is still 0. Let's make it, and again, just notice the kinetic energy, 0.5 joules before, 0.5 joules afterwards. Let's have a look at an inelastic collision where the balls will actually deform and stick together. Kinetic energy 0.5 joules before, kinetic energy afterwards is 0. So that's what you saw with that extreme head-on car crash. All the energy, all that kinetic energy goes into deformation and they don't bounce off at all. Now, of course, as we said, usually in the real world, collisions are maybe about half-half, depending on the materials, 0.5 joules of kinetic energy before and 0.12 joules afterwards. So a lot of kinetic energy was lost in that particular collision, but momentum was still conserved. The third example, where we have ball number 1 catching up with ball number 2, which is moving more slowly. Total kinetic energy before is 0.27 joules. In an elastic collision, all of that is conserved and the energy is the same afterwards as before. If we have an inelastic collision where the balls stick together, momentum will still be conserved, but kinetic energy goes from 0.27 to 0.20. So again, some of that kinetic energy is lost. If we have a collision which is a little bit elastic and a little bit inelastic, again, we go from 0.27 joules to 0.22. Not as much kinetic energy is lost, and the balls separate. So I hope this just makes it clear that in any collision, elastic or inelastic, momentum is conserved, but kinetic energy is only conserved in a perfectly elastic collision. Now you remember looking at Newton's cradle that if we drop one ball off, then just one ball comes off the other side as well for conservation of momentum. But think about what's happening next. Now I'm going to drop just one ball again from the left-hand side of the screen, but watch carefully what happens on the right. Did you see that 2 balls came off? And also that the energy is very quickly dissipated. Just watch again, dropping one ball, but 2 balls come off. Now, why did it happen that time? Well, it's simple because I've cheated. If you look carefully, you'll see I've actually stuck these last 2 balls together, put a bit of press stick between them so that they have to move together. So I've actually changed the collision from an elastic one to an inelastic one. And in that case, the rules are slightly different. And what you see very clearly is how quickly the energy gets used up compared with the elastic collision. And let's see the elastic collision one more time. I've removed the press stick now, and now you can see just one ball comes off, and you'll see it carries on moving for quite a lot longer because the energy is not lost in an inelastic collision. So before we get you to try some of the recent exam examples, question 4 on momentum, let me do an illustrative exam example for you. Now, when I introduced the section on solving equations, I showed you this question from November 2019. I'm not interested in solving this now, but what I wanted you to see is that when you look at the memorandum for marking, there's not only one solution. And you can see for this question, there was an option 1, there was an option 2 using completely different equations, and there was an option 3, which further split into 3 sections. So that's why it's really important for you to try these yourself, not just to focus on getting the right answer. You don't need me for that. You can just use the memorandum, but to focus on strategy and understanding the skills necessary so that you can't just solve this question, but that you can solve every type of question like this which comes up in the exam. And remember on page 37 at the start of this section on solving equations, I introduced my progress method. Now, of course, you don't have to use this every time, and if you're confident, that's fine. But if you're stuck, it will really help you to get started in solving a question. So P stands for picture. Draw a picture if it helps, and it often does in momentum questions, just to keep track of all the bodies, masses, and velocities. Check carefully what is required. In other words, what are they asking you for? Is it a velocity, a mass, a distance? Look out for what's obvious. For example, if they tell you something's at rest, then you will know that its initial velocity is 0. Check carefully what is given and make sure they're in the correct units, meters per second and kilograms. Then R stands for relate. Relate what is given to what is required by E, choosing the correct equation. Once you have that, you simply have to substitute and solve. Now, of course, we find our equation from the data sheets. We've already talked about that in this video. On page 38, page 1 of the data sheets, in the second block, the equations on force, you'll find the definition of momentum, P equals mv, the momentum impulse theorem, and a change in momentum. So make sure that you focus on the correct equations. And I really want to encourage you to do the exercise on page 40 to get to know the symbols, the quantities, and the units. So we're going to do an illustrative exam example. It is in your books at the bottom of page 51, but why don't you just watch how I do it on the screen, and then you can use that same progress method to tackle the recent exam questions. So this is question 4 from November 2017. The typical momentum question: a bullet is fired through a block. There's a 2-kilogram block at rest on a smooth, frictionless horizontal table. The length of the block is x. A bullet with a certain mass traveling east, you can use left, right, or west, east at 400 meters per second, strikes the block and passes straight through it with constant acceleration. Ignore any loss of mass of the bullet and the block. 4.1 is a recall question. I'm not going to deal with this now. But then you're told that afterwards, and it's shown on the picture, the block moves eastwards at 0.7 meters per second. You're asked to calculate the velocity of the bullet. Now, we should expect that to be less, because obviously it must have transferred some of its momentum to the block. Otherwise, the block would not be able to move at all. So we expect something less than 400 meters per second. And then you're asked to calculate the length of the block. So let's bring our progress method into play here. So a picture is normally given in the exam paper. Don't redraw it, you're wasting time, but sometimes it helps to add things. So like the mass of the bullet was not given on the picture, I just added so that all the information is there. I've used capital B for bullet and small b for block here. Work out what is required. Well, I've put it in green. You ask for the velocity of the bullet after it emerges. Calculate the velocity of the emerging bullet. What is obvious? Well, you're told there's no friction. Momentum is always conserved. And VBI, which is the velocity of the block beforehand or initially, is 0. What are you given? Well, you're told that the mass of the bullet is 0.015 kilograms. Mass of the block is 2 kilograms. The initial velocity of the bullet is 400 meters per second east, and the final velocity of the block is 0.7 meters per second, also eastwards. Now you must relate what has been given to what is required, and we need to find VBF, the final velocity of the bullet, in terms of those given quantities. You might be finding it a bit difficult to keep track of all the masses and velocities. That's why a before and after diagram is often very useful for this. So continuing with progress, we need to relate VBF, the final velocity of the bullet, to those 4 quantities that we know. And the equation is simply that momentum is conserved. So the sum of all the initial momenta is equal to the sum of the final momentum. So writing it out, for the bullet, mass times initial velocity, plus for the block, mass times initial velocity, which we know is 0, is equal to afterwards mass of the bullet times the final velocity of the bullet, that's what we're looking for, plus mass of the block times final velocity of the block. Substitute, put the numbers in place, and again, these numbers, they're easiest to find when they're written above the diagram. The mass of the bullet, velocity of the bullet before, mass of the block is 2, velocity is 0, so that term will disappear, but do write it in so you can get marked for it. Afterwards, mass of the bullet again, VBF, I've left it in green, that's what we're looking for, plus 2 kilograms times 0.7, you were told that's the final velocity of the block. So multiply it out, solve carefully for VBF, and you get an answer of 306.67 meters per second to the right. Don't forget to put that there. All the momentum was to the right initially, so all the momentum must be to the right afterwards as well. Remember, we said we expect something slightly less than 400 because the block would have slowed the bullet down, so you can use that to check your answer. Now, how is this marked? Well, first mark was for the momentum equation. Second mark actually for putting in the expanded version of the equation. Third mark for substituting in correctly all the numbers. Fourth mark for the correct answer, and also for the direction. So it was just 4 marks, and you need to be very careful that you got all of those correct. So the second part of the question, which is for 5 marks, calculate x, the length of the block, if the bullet travels for 0.002 seconds. Now, very often, the second part of a question will use something which you've calculated in the first part. First part asks for the velocity of the bullet afterwards, and so we expect that we're going to use that to calculate x. So once again, the picture's already there. I will just add the velocity of the bullet final. So the bullet's velocity decreases from 400 meters per second to 306.67. We're going to use that decrease to calculate the length of the block because we know how long that took. What's required is delta x, or just x, the length of the block. What's given, is that the initial velocity was 400, final velocity 306, and delta t is 0.002. So now we can look for an equation because we need to find delta x in terms of the initial velocity, the final velocity of the bullet, and delta t. Now, in this case, it's a good example of where you have to look for an equation somewhere else. In fact, we need to look under these equations of motion, not the momentum equations, to find what we need. And there you can see delta x, the length, in terms of initial and final velocity, and delta t, the time. So once we have the equation, we simply substitute our numbers in, initial and final velocities, and we're going to take an average, we multiply by delta t, and we get delta x is 0.71 meters. Now, how were the marks allocated for this? It was 5 marks, remember. 1 mark for finding the correct equation and writing it down. But remember, you only get that mark if you continue and substitute in. Just the equation by itself will get you no marks. Then 1 mark for putting in the velocities correctly. 2 marks for that, 1 mark for delta t, and then 1 mark for the final answer. Because it's just a length and there's no direction, there's no extra mark for direction. So this should give you a good idea of how to answer a typical momentum question. So let's take a look at the most recent exam question. So here's a snapshot of the question 4s from paper 1 from November 2018, 2019, and 2020. 2020 was a fairly standard collision between 2 balls. 2019 was a bullet passing through a fixed block. And 2018 was a girl on roller skates throwing a parcel away from her and consequently moving in the opposite direction. Now, as I've said many times in these videos, these exams will be of the most use to you if you actually try the question yourself first. So it's really important that you pause or stop the video here for 28 minutes while you try to complete the 3 questions on pages 50 and 51. Don't worry about November 2017 on the bottom of page 51, because we've done that already. So please pause this. There are 28 marks if you leave out the recall questions. Try them yourself before you watch my answers. Right, so let's look at the answers there. November 2018, a girl is on roller skates, initially at rest. She's holding a parcel of mass 8 kilograms, and she throws it horizontally to the right at a speed of 4 meters per second. Immediately after the parcel has been thrown, the girl roller skate combination moves at a speed of 0.6 meters per second, and you're told to ignore the effects of friction and rotation. I'm going to leave 4.1, which is a recall question. You can learn those yourself. 4.2, let's start with a simple 2-mark question. Will the girl roller skate combination move to the right or to the left after the parcel is thrown? Name the law in physics that can be used to explain your choice of direction. Well, she will certainly move to the left, and the law is Newton's 3rd law of motion. It's the action-reaction law. So the girl exerts a force which pushes the parcel away to the right, and therefore the parcel exerts an equal and opposite force which pushes the girl away to the left. Of course, the parcel will travel much faster than she does because it is much lighter. Then you're told the total mass of the roller skates is 2 kilograms. Now, please keep this in mind because 4.3 asks you to calculate the mass of the girl. So please remember you're going to have to subtract those 2 kilograms. So I've taken the picture from the exam, put down some of the initial conditions you were given. Please remember that that velocity must be negative. Now, of course, you can choose to the right or to the left as positive. I just suggest that in all your questions, you use upwards or to the right as positive. It keeps it simple. So let's look at our progress method. A picture is given, but the picture is only given for after. And so it can be quite useful to add a before picture, although it's very simple in that both initial velocities of A, the girl, and B, the parcel, are both 0. So therefore, the total momentum before the parcel was thrown is 0. So when we calculate momentum after, it will also have to be 0. That's why we need that negative sign on the velocity. It's obvious you're told there was no friction, momentum is conserved, and the 2 initial velocities are 0. What is given? Well, you're told the mass of the parcel, the mass of B. You're told the final velocities of the girl roller skate combination and the parcel. And you are asked to find the mass of the girl. And please remember to subtract the mass of the skates. So the required article is the mass of the girl, or MA. So we need to find MA in terms of what we have. So we continue to look for an equation. It's a simple equation, conservation of linear momentum. We write it out in full. In this case, just to make it easier to follow, I've put the masses in red and the velocities in black. And in green, we've got the mass of the girl roller skate combination, MA, because that's what we are looking for. So simply the sum of the 2 momenta before, which we know is going to be 0 because both velocities were naught, is equal to the sum of the 2 momenta after. So it's really quite a simple equation. The left-hand side reduces to naught because the initial velocities are naught. The right-hand side is the mass of the girl in roller skates times the velocity minus 0.6 plus the mass of the parcel, 8 kilograms, times the velocity 4. Solve for MA, and you get 53.33 kilograms, but the roller skates weighed 2 kilograms, so the mass of the girl will be 51.33 kilograms. Not too difficult. Mark allocation, 1 mark for the initial equation, 1 mark for the substitution on the left, 1 mark for the substitution on the right, and then, 2 marks for the substitution on the right for getting the 2 velocities, and then finally 1 mark for the correct final answer. So if you end up with 53.33, you're not going to get that final mark. 4.4, calculate the magnitude of the impulse that the girl roller skate combination is experiencing while the parcel is being thrown. Here's your impulse equation. Please remember, impulse is not force. Impulse is F delta T or delta P. So the magnitude of the impulse is delta P, and it's simply the mass of the girl times the change in velocity. The mass the girl roller skate combination, just the combination, 53.33. The final velocity was minus 0.6. Initial velocity was 0, and we get an answer of 32. Because you asked for the magnitude, you don't need to worry about a sign. The magnitude of the impulse is 32 Newton seconds if you're using the F delta T, or kilogram meters per second if you're using the momentum side. Now, the last question is only for 2 marks, and you're told without any further calculation, write down the change in momentum experienced by the parcel. Well, 4.4, that represents the change in momentum experienced by the girl roller skate combination. So therefore, the change in momentum experienced by the parcel must be equal and opposite. So it's 32 kilogram meters per second, or you can write it as Newton seconds, but you do need to specify that it is to the right, because the parcel was stationary and ended up moving to the right. So the change in momentum was in the direction towards the right. Let's have a look at the question 4 from November 2019. Slightly different question, and the conservation of linear momentum equation is not used in solving this one. But a bullet moves east at a velocity of 480 meters per second. It hits a wooden block that's fixed to the floor, which is stationary. Bullet takes 0.01 seconds to move through the stationary block and emerges from the block at a velocity of 80 meters per second. So you can imagine just going through the block, the friction pushing through the wood slowed the bullet down quite considerably. I'm going to do 4.1, which is a recall question. Then you're told the magnitude of the momentum of the bullet before it entered the block was 24 kilogram meters per second. 421, calculate the mass of the bullet. Now, we don't need a progress method for a 3-mark question. It's very simple. Momentum equals mass times velocity. So mass equals momentum over velocity. So 24 you were told is the momentum. 480 you were told is the velocity. Divide and we get the mass of the bullet is 0.05 kilograms. And remember, I said very often the answer of the first part is used in the second part, and this is indeed the case. 422, calculate the average net force exerted by the block on the bullet for 5 marks. So let's consider our progress method. Picture is given in the exam, don't redraw it, but I've just added the mass of the bullet and delta t, the time for which it travels through the block. Useful having them on the diagrams, they're easy to find. What is required is the average net force, which is F net. Not really anything obvious, perhaps just that the block is stationary. What you're given is the mass of the bullet from 4.2.1. You're told that the initial velocity of the bullet is 480 meters per second. Final velocity is 80, and delta t is 0.01 seconds. So in finding an equation, we need to relate F net in terms of those 4 variables that we know. So from the data sheets, we will find the impulse momentum theorem equation. F net delta t equals delta p. And of course, delta p is m times v final minus v initial. So we now have all the variables we need, and we can simply substitute in. Substitute the mass from the first part of the question, the final and the initial velocities, and then delta t. Now you'll notice we get a negative answer, and we've been taking motion to the right as positive. The negative force to the right is the same as a force to the left or in a westerly direction. How is that marked? Well, 1 mark for getting that correct equation there, 1 mark for delta t, 1 mark for putting in the velocities correctly, 1 mark for the answer 2000 newtons, and 1 mark for the direction, which could be west or left. Please don't leave out the direction. Now, this is not the only way to solve this. There are other ways, and you can refer to the memo for that. I'm not going to go through them. And I showed you before that we looked at option 1 here using the impulse equation, but you could do it using equations of motion or various different ways, even using change in kinetic energy. So please don't just focus on getting the correct answer. Focus on finding out how the answer was obtained so that you can do it again by yourself when you face a similar question in your exam. And finally, the November 2020 question 4. Fairly straightforward question. Ball P is moving to the right, ball Q to the left, they collide. After collision, ball P bounces back and moves to the left, and you're going to be asked about the velocity of ball Q after the collision. You're given various masses and velocities, and in fact, what I've done is to set up this exact situation in Collision Lab. I was able to put in the exact masses, the velocities I had to divide by 10 because the system didn't allow anymore, but it still gives you an idea of what would happen, which is useful. Now, it's particularly useful to look at this momentum diagram, and you can see that because of its larger velocity and its larger mass, ball 2 has a much bigger momentum. So in fact, the total momentum is to the left, and therefore the total momentum will have to be to the left afterwards. And so we suspect that ball 2 might move to the left as well. This is a very inelastic collision. You don't need to know that, but when I run the simulation, you can see what happens. Ball 2 moves more slowly to the left, as does ball 1. Let's do it in slow motion. And you can see they come together They collide. A lot of energy is lost in a collision. You can see from the kinetic energy. And so we expect to find a small negative velocity for ball 2 after the collision. Now, of course, you won't have the opportunity to use Collision Lab during your exam, but I think that is helpful to see how this collision would be in real life. So let's bring in our progress method. The picture is given, but it is quite useful to add the masses as I've done. They're the same on the left and the right, obviously. What is required is the velocity of ball Q after collision, so it's VQ final. What's obvious is there's no friction and momentum is conserved. What's given, you're given the two masses and you're given 3 velocities, which I've put in black to make them easier to read. And you simply need to find VQ final in terms of those 5 quantities you have been given. The equation is very simple, conservation of linear momentum. We put it in its full form there. And on the right, we've got VQ final, which is what you're going to be looking for. Fill in all the numbers, carefully multiply out and solve. Just remember that velocities to the right or east are positive. So like 10. Velocities to the left, like minus 15 and minus 5, must be negative. When you solve this for VQ final, you get minus 3 meters per second or 3 meters per second in a westerly direction or to the left. Now, how is this marked? 1 mark for the conservation of linear momentum equation, 1 mark for your substituting on the left, 1 mark for substituting on the right, 1 mark for the correct answer of 3 meters per second, and 1 mark for the correct direction. Not too difficult, you just have to keep track of all your quantities carefully. 422 said calculate the magnitude of the impulse on P during the collision. Now again, what's required is the impulse, and we know that impulse is F delta T. What we've been given is the mass and the velocities of P before and after. So in this case, you're not actually carrying a number through from part 1 to part 2. So we need to relate F net delta T to the mass, initial, and final velocity. So from the data sheets on page 38, we use our impulse equation, and we simply substitute in the mass of P is 0.16 kilograms. Now watch carefully, the final velocity of P is minus 5. The initial velocity is plus 10, and that's why you get minus 5 minus 10. When you multiply out, you get minus 2.4, but it just asked for the magnitude of the impulse on P. So we can just give it as a positive number, 2.4 Newton seconds for 3 marks. So I hope you paid attention to momentum, because if you don't pay careful attention to momentum, it has a habit of getting you into trouble. Momentum is all about collisions. And so make sure that you learn the section carefully, that you look at the equations carefully, and I'm sure that will put you in a very good position to answer question 4 and to get the marks, which is going to take you all the way towards a good matric qualification in science.